in a more better manner. But the only problem about first law of thermodynamics is though it talks about the flow of heat in terms of quantity, it doesn't help us understand the qualitative aspect of heat flow, because we have no idea, no way to determine whether or not the heat will flow under the given circumstances. For that, we need the second law of thermodynamics, which speaks of entropy and the free energy equations and everything. So
Exactly,
this
what do you mean by internal energy? Can you tell? Oh, what are the
the
things you know
internal
about?
energy is all of the you know energy which a system, I mean which the constituent molecules of a system will possess, other than the random vibrational heat energy. That is like, maybe internally the molecules are all having some sort of rotational energy, they're rotating about their own axis, or maybe there are two molecules which are rotating about a given center of mass, or maybe they have some sort of directional kinetic energy, not randomized, directional kinetic energy. Maybe they have some sort of potential energy. Maybe they have some sort of mechanical stress energy, maybe due to some sort of mechanical strains produced in the system due to its configuration. Maybe they also have, uh, like maybe some of the electrons might tend to from a given orbital to another orbital and release energies which they are continuously absorbing and releasing energy in different forms. All the sum of the other forms of energy, basically, other than heat, which is found in the system, is internal energy.
Good. Uh, Internal energy is a property. It is a point function or path function.
Sir, internal energy is a, uh, I think it's a point function.
Point functions. Okay. Good.
Yeah.
Purti. Purti. Purti Devi.
Good morning, sir.
Good morning. What are the things you know about steady flow energy equation? Already studied. I am doing revision on first law of thermodynamics. Okay. Can you highlight what are the things you studied in first law of thermodynamics? Application of first law of thermodynamics. Okay, in the yesterday's class, I'm doing revision on first law of thermodynamics. In yesterday's class, I discussed what is Joule's experiment, what is the first law of thermodynamics, and then the first law of thermodynamics for various energy interactions. Like, so if there are more than one work transfer and heat transfer, how to take the first law of thermodynamics, that is Q equals to delta U plus W. Okay, these are the things I discussed in the yesterday's class. Okay, today I'll discuss the application of first law of thermodynamics. Okay.
Sir, at what speed
Yeah.
will you consider air to be compressible? Like, suppose air is flowing at certain velocity. Okay.
Mm, mm,
So, if air is flowing at certain velocity, we know that based on the velocity, and if it is a steady state flow, the
mm.
pressure decreases. That is the basic concept behind lift
No, no,
produced in planes,
no,
right?
no. Air compressor pressure increases, right?
No, no, sir, not compressor. I'm talking about the Magnus effect. You know the Magnus effect, right? Or do
Tell
you
me.
know about the aeroplane lifting effect? Where,
Aeroplane lift. Tell me.
yeah, yeah. So that one
Mm,
I'm talking about.
mm,
So suppose there is a pipe, and in the beginning of the pipe there is a, say, very, a large cross sectional area it has, and at the mouth of the pipe it
mm,
has a very tiny cross section, and
mm,
a steady state flow of
mm,
air is happening through that
mm,
pipe. Okay,
mm,
so
mm,
naturally, because of equation of continuity, at the mouth of the pipe, the velocity of the air will become too much, right?
mm,
Compared to the velocity with which it is entering, to ensure
mm,
the mass flow, volume flow rate remains steady.
mm,
So, because the volume, I mean, velocity is very high at the mouth, the pressure
mm,
will decrease, correct?
Correct.
Pressure exerted by the air will decrease.
Mm,
So, like, at what speed should that air travel at the
mm,
mouth, basically, so that it becomes pretty compressible in nature.
mm. Okay, actually, you
Pressure.
are going to learn
Yeah.
drag force and lift force in fluid mechanics in fourth semester. Actually,
Okay.
we are having a certain formula for that one. Okay,
Okay.
Using that formula, you can calculate. Okay, we are having a lift force and drag force. One is acting in the direction of motion of air, and one is
Okay.
acting perpendicular to the motion of air.
Hmm.
Okay, based upon that one, you can calculate the velocity. That is one is lift
Right.
force and one
Imagine.
is drag
Yeah.
force.
And one more question I had, sir. Suppose there is a box. Okay.
Mm, mm,
Box filled with air, sealed on
mm,
all sides. Okay. And what I'm going to do is, with
mm,
a pin, I will make a tiny hole on the
mm.
side of the box.
Okay. Mm,
Very tiny hole. Okay. And then what I will do
mm,
is, it's a very nice and flexible box, maybe made of plastic. I'm going to squeeze the box really hard. Okay.
mm, mm,
So when I squeeze the box really hard, pressure is applied on the interior, right? On the
mm,
gas, air
mm,
present inside. So
mm,
through that hole, we will see the air flowing at a very fast velocity, again
mm,
due to the equation of continuity, right?
mm.
So
Yes.
in such a scenario, is it okay for me to apply Bernoulli's principle?
Bernoulli's principle. Okay. Bernoulli's principle. We are having certain assumptions. It comes in fluid mechanics actually. If the flow is incompressible, but air is compressible, right? We
Yeah, but
cannot apply the Bernoulli's equation for compressible fluids because density varies from point to point.
suppose like at small scales,
Uh,
okay, like at
mm.
regular scale,
Mm.
everyday life scale, we can approximately apply, no, sir.
No, actually,
Suppose I'm
according
not
to the
very.
Bernoulli equation states
Hmm.
that P by rho g plus V square by 2g plus z equals to constant for incompressible, irrotational, steady flow actually. So mainly we derived derivation for this one only, for incompressible flow only, for water only. Okay.
Hmm.
This actually what your question, what actually I did not get properly. Can you ask once again?
Yes, sir. Suppose there is
Mm.
a plastic bottle. Take a
Mm.
plastic bottle.
Mm. Mm.
Suppose you make a very tiny hole on its side. It is
Ah,
closed basically.
okay.
Plastic bottle is closed in the beginning. It is filled with air only at normal atmospheric pressure. You make a very tiny hole on the side of the bottle with a pin. So and then you squeeze the bottle. So you
Mm.
expect the air to come out with a high velocity from the hole, right?
Mm. Mm. Correct.
So suppose I'm
Mm.
not very much worried about the say accuracy of my calculations. Suppose I have a very
Mm.
high tolerance for the errors. Okay, suppose I can take an error of very 20 meter per second also, no problem. Let us say.
Mm. Mm.
Then in that case where the accuracy is not that important, can I
Mm.
still apply approximately Bernoulli's principle? Very
No,
very
no,
approximate.
no, 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 not possible. Not possible. You cannot apply Bernoulli's equation because
Okay.
there will be variations of parameters like pressure head, velocity head, and kinetic head, datum head. All
What
variations
kind of what
takes
kind
place.
of
Uh,
variation do you expect, sir, for a compressible fluid? Do you
okay.
expect a negative variation or a positive variation?
No, actually, the parameter should remains constant for this one flow. Then only the Bernoulli equation is holds good. Suppose there will be variation, okay, because all the parameters like the velocity, pressure, and then the datum head, pressure head, velocity head, these are constant at a particular point from one point to another point. But in case of this one, what you are talking on is not applicable actually. It's not holds good Bernoulli equation. Approximately also you cannot apply
Okay.
because of the variation of the parameters.
Hmm.
And even you are making the whole means once again there will be variation, okay, from system and surroundings and within the system also there will be variation, okay. The heads, whatever we are dealing with, we are mainly dealing with the three heads in Bernoulli's equation. One is velocity head, a pressure head, and this one datum head, okay.
Yes, sir.
All these heads should be constant for whenever we are going to deal with Bernoulli's equation. Okay, in your case, I think the parameters are varying. Okay, from point to point, and also from system to surroundings. Okay, I think Bernoulli equation not holds good in this case.
So what kind of variation can you expect, like approximately?
Where
Suppose, so
mainly pressure, velocity, and this one datum like
that's what. So,
position. Hmm.
like suppose according, let us say, at the mouth where the cross section is narrow,
Hmm.
according to Bernoulli's principle, first I have calculated some values I have got. So
Hmm.
in real life, what kind of variation from those values will I see? Will I see a positive variation in the sense, will I see a value which is more than what I have calculated for air, or will I see values which are less than what I have calculated? That is a negative variation. For air, what do you
Negative,
expect?
negative will not get. You'll get positive only. Positive
Okay,
variation.
so you'll get a bit more than what you have
Yeah,
calculated.
yeah. You'll get more
Okay,
variation. Positive variation only, not negative.
okay, yeah, okay. So that's what I wanted to know actually. Yes,
Positive variation
thank
only
you.
you get it.
Hmm. Okay, okay, sir. Thank you very much. That's the question I had.
You are doing analysis on this one, fluid properties. Huh?
Very needed for
Uh,
my system 7
uh,
project, the modified
okay.
elevator system,
Okay.
dampening system of the elevator, which I
Mm.
discussed with the judges
Uh,
yesterday. So I was thinking it needs a fluid, okay, and it
mm.
uses the steady state flow equation.
Actually, whatever your project notes mainly related to fluid mechanics, you are learning entire thing in fluid mechanics that comes in fourth semester actually.
Yes, sir. We plan to continue the project
Whatever
for the
concepts
next
you are
year.
having, all the things you are learning in fourth semester fluid mechanics.
Okay.
Everything, the fluid properties, the Bernoulli's equation, compressible fluid, incompressible fluids, laminar flow, turbulent flow, then flow through pipes, Magnus effects, then Reynolds number, all dimensions, all the things you are going to study, everything is there in fluid mechanics. Okay.
Yes, sir. That's why we are
So
planning to continue the project into next
yeah, yeah,
semester to
yeah.
make
So
it
it's very
21 days.
good
Thank you.
actually. So whatever things you are planning, no, all the things you are learning in sorry, fluid mechanics that comes in fourth semester actually.
Yes, sir. That
Mm.
is what I.
Okay.
That's all.
Now I'm doing steady flow energy equation. Okay, steady state means the thermodynamic properties are invariant with respect to time. Remember steady flow. Okay, and we are having a separate subject called as heat and mass transfer in sixth semester. So we are having a heat transfer lab also there. So you are not going to start your experiment immediately, because once you switch on the motor, okay, so that will not get the steady state. You have to wait for half an hour or 45 minutes like that. So it means it should attain the steady state. Okay, then only we are going to start the experimentation. Like we are having thermal conductivity, then fin apparatus, then refrigeration, air conditioning, then we are having a heat exchanger apparatus. So there, so the steady flow plays a very important role. Okay, steady state means the thermodynamic properties like pressure, volume, temperature, etc. They are not varying with respect to time, so that they are invariant with respect to time. That is called as the steady state. Okay, steady flow energy equation applied in mainly flow process in many engineering plants. Okay, so such as compressor, condenser, boiler, turbine, nozzle, and pump. Okay, before studying, so you should have the idea of all these devices. Okay, turbine already studied in elements of mechanical engineering. A turbine is a power generating device. Okay, power generating device, that is the mechanical energy is converted into the electrical energy. Okay, so for example, in case of hydraulic turbine, so the input is the potential energy of water is taken to the turbine blades. Okay, so where the turbine blade starts rotating, and the potential energy is converted into kinetic energy. Okay, as the turbine blade starts rotating, the shaft connected to the rotor also starts rotating. Then there will be conversion of kinetic energy into the mechanical energy. Okay, and then the electrical generator is coupled to the shaft. mechanical energy is converted into the electrical energy, then that electrical energy is going to supply to the places where it is required. So how the conversion of the energy takes place in case of turbine. Turbine is a power generating device. Work is done on the system. So we are having different types of turbine. One is the hydraulic turbine where the working fluid is water. Second one is steam turbine where the working fluid is steam. And third one is the gas turbine where the working fluid is gas or air. In gas turbine we're having two types. One is the open cycle gas turbine and second one is a closed cycle gas turbine. And in hydraulic turbines we're having the impulse turbine and reaction turbine. So impulse turbine is nothing but your Pelton wheel. So we are having two types turbine, impulse and reaction. In case of impulse turbine, the only the kinetic energy is available at inlet to the turbine, and in case of reaction turbine, both kinetic energy and pressure energy is available at inlet to the turbine. It's all about turbines. So you are having separate experiments on turbines in fluid mechanics lab in fifth semester. Okay, and you are going to studying turbo machine. Okay, there you are studying turbine in detail and turbo machines, that is in fifth semester. Okay, so turbine is a power generating device where the potential energy of water is converted into mechanical energy, which in turn converted into the electrical energy. That is all about turbine. Okay, next we are having the compressor. Compressor is opposite to that of turbine. Okay, it is a work absorbing device. Okay, so we need power to drive the compressor. Okay, I think you might have studied in open cycle gas turbine. We are having first compressor, then we are having combustion chamber, and then turbine. Okay, so the compressor is a power absorbing device. The work is done on the system, that is W is negative. Okay, we are having different types of compressor. That is reciprocating air compressor and rotary air compressor. Okay, and then also single stage, multi-stage. Once again, you are having the compressor experiment in fluid mechanics lab. Okay, so it is work absorbing device. Okay, and next we are having the boiler. What do you mean by boiler? Anybody? What is the application of boiler?
So producing steam.
Producing steam. So okay, so the producing the steam at a constant pressure. Okay, the heat is supplied. It is a closed metallic vessel where the steam formation takes place from the water at constant pressure, and the heat is going to supply the externally or internally. You study different types of boiler, like internally fired, externally fired boilers. Okay, that Lancashire boiler, Lamont boiler, etc. It is a steam producing machine from the water. Next, we are having the condenser. Condenser is a device. There will be a change in phase takes place from vapor to liquid. Condensation. Okay. And then one more is that evaporation. Evaporation means where the change in phase from liquid to vapor. Okay. So condenser. Next, we are having nozzle. Okay. Nozzle is mainly used to increase the velocity of working fluid. Okay. So with the expense of pressure energy, the velocity increases. Okay. Nozzle, and one more thing you should remember, it is neither work producing nor work absorbing device. Means W is 0 and Q is also 0 because there is no heat interaction between system and surroundings when you are going to mount this nozzle with a adiabatic wall. Okay, so the nozzle is neither work producing nor work absorbing or heat producing or heat absorbing device. Nozzle is mainly used to increase the velocity of working. Okay. And one more device is that, can you tell, do you have any idea the instrument which decreases the velocity? Which instrument? The nozzle is used to increase the velocity. Can you tell which instrument decreases the velocity of working fluid?
So some sort of dissipator or something.
That is called diffuser. You remember, nozzle is used to increase the velocity. Diffuser is used to decrease the velocity. Okay. So in case of a nozzle, pressure decreases, the velocity increases, and in case of diffuser, pressure increases, velocity decreases. Okay. So that is nozzle and diffuser. And pump. Okay. So pump is another important mechanical device. So where mainly used to lift the water or any working fluid from lower level to higher level. Okay. So once again, it is a work absorbing device. So W is negative. Okay. And once again, it is opposite to that of turbine. Okay. It is a work consuming device. Pump. We are having a centrifugal pump and we're having a reciprocating pump. Okay. So where the electrical energy is converted into the mechanical energy. Okay. And in case of turbine, mechanical energy is converted into electrical energy. In case of pump, it is the reverse. That is, electrical energy required to run the pump is converted into mechanical energy. That is hydraulic energy. Okay. Now we are going to study the compressor. First, as I said, it is a device used to compress the fluid and deliver it at higher pressure and large flow rate. There are two types of compressor. One is rotary compressor and reciprocating air compressor. The rotary compressor are used to develop the high pressure and have a rotor. Okay, that's why it is called as rotary compressor as their primary element. And in case of reciprocating air compressor, we are having the piston cylinder arrangement. Piston reciprocates inside the cylinder. Once again, we're having the inlet valve, delivery valve, like that. It is very similar to our internal combustion engine. Whatever reciprocating pump is similar to our IC engine compressor. Okay, so we are having rotary element in case of rotary compressor. That's why it is called as rotary compressor. And here the assumptions are most important. So as I said, the work done on the system, so the W is negative, negligible change in potential energy. Okay, and heat is lost from the system is negative. Okay, and you see the steady flow energy equation. This is called as the compressor. And one more thing. So this while drawing the diagram, you have to show compression. Okay, so at the starting, you have to draw a bigger line, and then it is decreasing order. Okay, it is compressing. Okay, you have to show like this compressor pump, like that. You have to show in the decreasing order. Okay, I'll show the another diagram for turbine. You see, for turbine, you should show in the increasing order. This is a notation. Suppose if you make any mistake, you lose the mark. I'm telling you, so that this diagram is also most important. Turbine is a expansion device, expanding device. So the work done is positive. That's why. So you have to show at the beginning it is a small line, and at the end you are having a bigger line. So in case of work absorbing device, you have to show in the different order. Okay. So starting you are having the bigger line, and then it decreases towards at the end. So it is the air compressor. Okay. And then for all the application, first you have to write the steady flow energy equation. As I said, there are two forms of steady flow energy equation. You see, okay, H1 plus GZ1 plus V1 square by 2 plus Q12 equals to H2 plus GZ2 plus V2 square by 2 plus W. Remember, this is the expression for standard steady flow equation. Okay, H1 is the enthalpy of working fluid, that is U1 plus P1 V1. You remember, H is the enthalpy. It is also property. It is given by summation of internal energy and product of pressure and volume. So H1 plus GZ1 plus V1 square by 2 plus Q122 equals to H2 plus GZ2 plus V2 square by 2 plus W. Okay. So for all the application, you have to write the steady flow energy equation, and then you have to read the term. You have to write the assumption. Okay, as I said, W is negative. Okay, W is negative, so you have to show minus. Okay, and then Z1 and Z2 are same, neglecting the datum head. Okay, that is Z1 and Z2. Suppose you take the datum line in center line, means that Z1 and Z2 remain same, and Q. Okay, so suppose if you're not providing with adiabatic wall, the heat is lost to the surroundings. Okay, so you have to take Q as minus. So M into H1 plus V1 square by 2, neglecting Z1 and Z2, minus of Q, M into H2 plus V2 square by 2, minus W. So after simplifying, so we'll get this equation as our aim is to find out the expression for W, because it is a work absorbing device, M into H2 plus V2 square by 2 minus M into H1 plus V1 square by 2 plus Q. Okay. Suppose if you change, if the velocity at the inlet is same as that of the velocity of outlet, or suppose if there will be a little bit variation, in that case we can neglect this velocity term also. Okay, so you remember the velocity plays very important role in case of nozzle. Okay, that nozzle you have to consider velocity, but in this case the almost whatever the velocity at entry and the velocity at exit are almost same. Okay, so little bit variation, so we have to neglect this one, and then after and suppose if we are providing the adiabatic wall, in that case we are going to neglect the Q also, and final expression is W equals to M into H2 minus H1. So this is the expression for the steady flow energy equation in case of rotary air compressor. Okay, in exam they give, so give the application of steady flow energy equation for the following device, like first one turbine, second one condenser, third one compressor, fourth one nozzle, fifth one throttling device, then so many things like that. First, don't derive the derivation. Okay, first you have to write the steady flow energy equation for all the application, and then you have to write the assumption, what are the things you are going to assume, then you have to neglect them. After neglecting them, you have to write the final equation. This is the expression for the steady flow energy equation for rotary compressor. In case of reciprocating air compressor, okay, it is also the same thing as that of your rotary compressor, but okay, we are having the piston cylinder element instead of rotary element in case of reciprocating air compressor, but the assumptions are same as that of the rotary air compressor. Okay, the work done on the system is negative. Okay, the negligible change in potential energy. Okay, and heat loss from the system to surroundings. Okay. Steady flow energy equation, as I said, so don't write directly this equation. First you have to write the equation, that is M dot into H1 plus V1 square by 2 plus Z1 G plus Q1 to 2 equals to M dot into 2 plus V2 square by 2 plus Z2G plus W. Okay, so first you have to write that equation, then after that we are going to reduce the equation like this: M into H1 plus V1 square by 2, so minus Q equals to M into H2 plus V2 square by 2 minus W, same as that of our rotary air compressor. So if change in velocity is negligible, assuming that V1 is approximately equals to V2, then we are going to neglect this one. Whenever it is okay, in that case, the V1 and V2 are neglected, and final equation is M into H2 minus H1 plus Q, where M is the mass flow rate. Okay, we are going to express in terms of kilogram per second. H2 is the final enthalpy, and H1 is the initial enthalpy at section 1, and Q is the amount of heat transfer. Next, I am going to discuss the turbine. Okay, turbine is the most important. Every time we used to ask the turbine. Turbine is a device which converts the thermal energy into useful work. Okay, so here first you have to write the steady flow energy equation. It is M into H1 plus GZ1 plus V1 square by 2 plus Q equals to M into H2 plus GZ2 plus V2 square by 2 plus W. Okay. So here Okay, after writing the steady flow energy equation, you are going to do the assumption. Okay, so anyhow, W is positive because it's a work generating device. You have to take W as positive. Okay, and then you have to take Z1 and Z2, neglecting uh, the datum. Next, assuming that V1 and V2 are same. Okay. And Q, suppose you are provided with the adiabatic wall. In that case, we are going to neglect. Okay, first, you neglect the main parameters like W first. Next, we are going to neglect the Q. Okay. Next, we are going to neglect V1 and V2. Okay. And then we are going to neglect the Z1 and Z2 also. Okay. So after neglecting the term, we are going to get the expression as M into H2 minus H1. Okay. You remember because in mm, numericals, they'll ask, okay, problems on compressor, problems on turbine, problems on nozzles like that. Okay, once you remember this equation easily, you can apply the equation and you apply this equation directly in the problem. Third device is our nozzle. They say nozzle is a device of a varying cross section called as convergent divergent nozzle. What you are seeing on the screen is it is a convergent divergent nozzle. It is used for increasing the velocity of flowing steam at the expense of pressure drop. Okay. Pressure decreases, the velocity increases. Okay. So one more device we are having that is called as diffuser. In the diffuser, uh, there will be increase in the decrease in the velocity with the increase in the pressure. You remember there is the opposite to that of nozzle. Okay. In the nozzle, pressure energy of fluid is converted into kinetic energy, and the nozzle is mainly used in turbines, fuel pumps, and jet engines mainly to get the high velocity of the working fluid. Next, regarding the assumption, first you have to write the standard equation, that is m into h1 plus gz1 plus v1 square by 2 plus q equals to m into h2 plus gz2 plus v2 square by 2 plus w. So you have to write the standard equation for all applications. Now we have to neglect the terms. Okay, as I said, nozzle is neither work producing nor work absorbing device. So W is 0. And then there is no flow of heat between the system and surroundings, that is Q equals to 0. And then Z1 and Z2 are also same, considering the same datum line. You see the datum line, Z1 and Z2 are same. Okay, and then you have to neglect the term here. Q is 0, W is 0, and then Z2 and Z1 are 0. Okay, so H1 and H2 you have to consider, V1 and V2 you have to consider. Okay, so so because M is same. Okay, steady flow means mass flow rate. We studied continuity equation, that is mass flow rate at the inlet equals to the mass flow rate at the exit. That is continuity equation is A1 V1 equals to A2 V2. Okay, you are going to study in fluid mechanics. That M dot or M gets cancelled on both sides. So we'll get H1 plus V1 squared by 2 equals to H2 plus V2 squared by 2. Okay, and our if velocity at inlet is known, okay, then we are going to find out the velocity at exit. Our aim is to find out the velocity at the outlet or at the exit. So V2 equals to square root of 2 into H1 minus H2 plus V1 square. Okay. And you remember that sometimes the velocity at inlet is too small as compared to the velocity at exit. Okay, suppose I'm having the velocity at inlet is around 10 meter per second, and I'm having the velocity at exit is around 600 or 700 meter per second. In that case, it is far greater than at the exit. Okay, in that case, we are going to neglect V1. Okay, if the velocity at inlet is too small as compared to the velocity at exit, in that case, you neglect this V1. Okay. Otherwise, suppose V1 is given in the problem, so directly you can find out the V2 using the formula 2 into H1 minus H2 plus V1 square. Can you anybody tell how to calculate H? What is the formula for enthalpy? Anybody?
What, sir?
What is the formula for enthalpy? H1, H2, what you are seeing? No. What is the formula for enthalpy?
So it's the sum of internal energy and the product of pressure and volume.
One more formula is there. Do you remember I explained in ideal gases? What is the one more formula? One more formula, standard formula. You remember H equals to MCP into delta T. Remember, whatever process it is, okay. The standard formula for enthalpy change is given by MCP into delta T, where M is mass of the working fluid, CP is specific heat at constant pressure, and delta T is the change in temperature. It's a standard formula for the enthalpy, okay. Similarly, we are having the internal energy formula also. Okay, yeah, internal energy is mCV into delta T. You remember these are the two standard formula we are going to apply for all the chapters. Okay, so and irrespective of the process, you have to use this standard formula. You remember H equals to mCP into delta T, where Cp is specific heat of the gas or working fluid at constant pressure. Delta T is final temperature minus initial temperature, and M is mass of the gas. Similarly, the change in internal energy. Okay, so you are learning in the third module and fifth module. The change in internal energy is given by mCV into delta T, where M is mass of gas, CV is specific heat at constant volume, and delta T is temperature. Okay, I'm telling again and again because in all the problems they used to ask this one: find out work done, find out heat transfer, find out change in internal energy, change in enthalpy, change in entropy. These are the 5 parameters you should remember. First one is work done. Second one is heat transfer. Third one is change in internal energy. Fourth one is change in enthalpy. And fifth one is change in entropy. Okay. Already we discussed all derivations and everything. So meantime, I am remembering you. You remember these two formula. H equals to mCP into delta T, because sometimes they won't give this formula in the problem. Suppose if you are not remembering, then in that case, it is very difficult to proceed. That's why remember the formula and proceed.
Yes, sir.
Next, pump. Pump is a device which takes the fluid from a lower level and delivers to a higher level. Okay. Um, the characteristic feature of pump are follows. Okay. The flow is adiabatic. Okay. There is no heat transfer, no change in internal energy. Okay. Work done on the system. This is most important. Okay. So in case of power absorbing device, W is negative, and in power generating device, the W is positive. Okay. So in case of pump, in case of compressor, we are having blower. Okay, where W is negative, that is work is required to run the machine, that is work done on the system. Then after that, you have to write the standard formula. M into H1 plus GZ1 plus V1 square by 2 plus Q equals to M into H2 plus GZ2 plus V2 square by 2 plus W. Okay, then after writing the equation, you have to do the assumption. First assumption is W is 0, Q is 0. This is the most important thing. Okay, pump is neither work, W is negative, Q is 0. Okay, and then Z1 and Z2. So because it is lifting the water from lower level to higher level, definitely you have to consider the datum head. Okay, Z1 and Z2 are different. Suppose I am taking from the bottom line, so Z1 is inlet and outlet is different. In that case, definitely you have to consider the datum. You don't neglect the datum here. You have to neglect datum in case of a nozzle, in case of a compressor, in case of a turbine. But in pump, you have to consider the datum. Okay, Z1 plus V1 square by 2. Okay, and then Q we can neglect because there is no heat transfer. So M into H1 and H2 also we can neglect. Okay, that is change in enthalpy U1 MCP into delta T. That is U1 plus P1 V1. Assuming the flow work remains same, so H1 and H2 are also uh, neglecting. Okay. So remaining thing is in case of pump you can neglect that assuming that P1 V1 and P2 V2 are approximately same because there is no compression. Okay, so we have to neglect flow work. That is parameters enthalpy. Enthalpy is anyhow MCP into delta T because it does not depend upon the temperature. Okay, it's independent of temperature. That's why you have to neglect the H1 and H2. Okay, so keep in mind H is MCP into delta T because no temperature term related to our centrifugal pump. It is not of important thing, so you have to neglect H1 and H2. So M into GZ1 plus V1 square by 2 equals to GZ2 plus V2 square by 2 minus of the. It's the expression for pump. Okay. Okay. So here, what we are seeing, it is a boiler. Okay, boiler is another important mechanical device. It is used for generation of the steam. Okay. So here we are going to generate the steam at 100 degrees Celsius. Okay, whenever you heat the steam above 100 degrees Celsius, that is called as superheated steam. In all the industries, superheated steam is used. Okay. Next, related to our steady flow energy equation. Okay, M. First, you have to write this M into all these parameters. Next, no mechanical work. Okay, there is no work done. Okay, so neither work producing nor work developing device, but turbine is work generating. But there is no work done at all. So Q you have to consider because the heat transfer is most important in case of boiler. Okay, because the heat is supplied externally. Hence, you don't neglect the term Q in case of boiler. You can neglect Z1 and Z2. Okay, so there is no mechanical work. W is 0. No change in kinetic and potential energies because the Z terms and V terms are to be neglected. Okay, that is Z1 and Z2, approximately same. And you have to consider the H1, H2, and Q. These are the three important parameters in boiler. Okay, because the H is, as I said, MCP into delta T is related to temperature. Q is also related to the temperature. Okay, so these are the three parameters you have to consider in the boiler. Okay, so while deriving the derivation, first you should keep in mind. So, what is the device? What are things to be neglected? What are the important parameters? Like that, you have to remember here in boiler the H1 enthalpy, H2 enthalpy at outlet, and then heat transfer are most important. Considering these three parameters, we can write the equation as H1 plus Q equals to H2 minus H1. So Q equals to H2 minus H1. In case of a boiler, the amount of the heat transfer is equals to the difference in enthalpy. That is the enthalpy at outlet minus enthalpy at inlet. You can write MCP into T2 minus T1. This is the expression for the steady flow energy equation in case of boiler. Okay, throttling process. Throttling process, you are going to study the throttling process is nothing but our expansion process only. Okay, we are going to study the throttling process in case of refrigeration process. We are having the four components. One is compressor, second one is evaporator, third one is throttling valve, what we are discussing here, and compressor, evaporator, throttle valve, and one more is condenser. Okay. These are the four devices we are going to use in refrigeration. Okay, so throttling device. Throttling devices means reducing the pressure. It is like expansion device. Okay. The steady flow energy equation is H1 plus GZ1 plus V1 square by 2 plus Q equals to H2 plus GZ2 plus V2 square by 2 plus W. Okay. Next, we have to neglect the terms. Okay. Here, the V1 and V2 are approximately same. Neglecting kinetic energy term, neglecting the potential this Z1 and Z2, and then we have to consider H1 and H2, and Q and W are neglected because it is neither work generating nor work absorbing, or there is no heat transfer. So finally, we are having H1 equals to H2. Whatever the enthalpy entering in case of expansion device equals to the enthalpy of the working fluid leaving the system. And we know that, okay, see the formula H equals to Cp into delta T. That is the standard formula for enthalpy. H equals to Cp into T. That you have to apply for the enthalpy at inlet and enthalpy at outlet. So Cp into T1 equals to Cp into T2. So Cp and Cp gets cancelled. We are having the T1 equals to T2 or H1 equals to H2 in case of throttling process. So the temperature of the working fluid at the inlet is same as that of the temperature of the working fluid at the exit. It's related to throttling process. Okay, so the most important concept, okay, the application of steady flow energy equation. Okay, they'll ask in the final exam as well as also these concepts are helpful for your competitive exam. Okay, so they'll give one problem on expansion valve. Okay, so you have to find out. Okay, using this formula, you are going to find out. Okay. Okay, guys, I'll stop the session. Any doubts in this steady flow energy equation? Okay. Any doubts? Suppose you're having any doubts, please ask me.
No, sir.
Okay. Okay, I'll stop the session now. Okay. So once again, you concentrate on this steady flow energy equation. Suppose if you are having any doubts, please let me know. Meantime, you try to solve problems on steady flow energy equation. Okay. Tomorrow I'll do the problems on steady flow energy equation. How to solve the problems.